about. The next section you would have done is transformations of functions. So function g at x is a transformed version of the function f at x, but these parameters a, k, d, and c are going to transform the graph of the function f at x. So just a quick review of what these parameters do. So if a is between -1 and 1, we say that that's a vertical compression by a factor of a. If a is bigger than 1 or less than -1, we say it's a vertical stretch by a factor of a. And if a is negative, it's a vertical reflection. The x-axis acts as a mirror, and it's flipped across the x-axis. Now let's look at the k value. K is kind of the opposite of the a value. So if k is between -1 and 1, that's going to be a horizontal stretch by a factor of 1 over k. The k value always gets flipped. We need the reciprocal of the k value. If k is bigger than 1 or less than -1, that's actually a horizontal compression by 1 over k. And if k is less than 0, we say that's a horizontal reflection. The d value, if d is bigger than 0, it goes to the right d units. If it's less than 0, it goes to the left d units. C, if it's bigger than 0, it goes up. If it's less than 0, it goes down. So let's do a quick transformations question for a radical function. So we have g at x is equal to 2 times the square root of -2 times x plus 1 minus 3. So basically we had the parent function, I'm going to call it f at x. We had the parent function root x. And then a bunch of transformations were done to this parent function of root x. What transformations have happened? Let's start by listing out really quickly those transformations. So the a value was 2. That does a vertical stretch by a factor of 2. So what happens is that doubles all the y values. Our k value is -2. That does a couple things. That does, since it's negative, that does a horizontal reflection. And the fact that it's less than -1 tells us that there's going to be a horizontal compression by a factor of always the reciprocal of the k value, 1 over 2. So I need to do these two things. I need to horizontally reflect it and do a horizontal compression by a factor of 1/2. To do those two things, I would divide x by -2. What else is happening? So our d value, it's always the opposite sign as what you see. Our d value is -1, so that means move it to the left 1 unit. To do that, I have to subtract 1 from all my x's, and our c value is -3. That means move down 3. I'd accomplish that by subtracting 3 from all the y's. So those are the transformations, and we're going to do the transformations to root x. So let's just get some key points to remember what root x looks like. So let's pick values for x. You can pick whatever you want, but the easiest values to pick would be perfect square numbers, because we can then square root them and get integer values. So 0 is perfect square number, 1, 4, 9. And to get the corresponding y's, just square root each of them. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. Oops, I wrote 9. Square root of 9 is 3. So what is this parent? We call this the parent function. What does it look like? It looks like this. And this function only exists, I didn't draw that very well, it should be curved smoothly. This function only exists to the right. Right? We can't square root a negative number. That's why I didn't draw an arrow to the left of this initial point here. It doesn't. When x is -3, the function doesn't exist. You can't square root -3 and get a real number. So this is what the parent function f at x looks like. If we want to know what the transformed function looks like, what we're going to want to do is do these transformations to the points of the parent function. So the x values, we need to divide by -2, and then subtract 1. And the y values, what we're going to have to do is double them and then subtract 3. So we need to double the y values and then subtract 3. So if I do these transformations, so the x values, so each of these x values divide them by -2, and then subtract 1. So 0 divided by -2 is 0, subtract 1, -1. 1 divided by -2 is -0.5, subtract 1, -1.5. And hopefully you see how that's working. If I keep going, I would get these points here. To get the y values, just take the y values of the parent function, double them, then subtract 3. So 2 times 0 is 0, minus 3 is -3. 2 times 1 is 2, minus 3 is -1. And then if we keep going, we would get these points. And now we can graph, this is our transformed function, g at x. We can graph g at x. So g at x, we have a point at -1, -3. We have a point at -1.5, -1, at -3, 1, and -5.5, 3. So our function looks like this, and this is g at x. Notice it's been flipped horizontally, right? So that's our horizontal reflection. Instead of going to the right, it's now going to the left. That's what our transformation told us. It's also been moved down and to the left, right? Left and down. And it's been horizontally compressed by a factor of 1/2. Next, exponential functions. So the general equation for exponential functions is y equals a times b to the x. So what do these parameters mean? So a, we usually call your initial value. B is your growth or decay factor. And x is the number of growths or decays. I'll just write growths. And we can calculate it by doing total time. So I'll write x equals divided by time it takes for one growth or decay. Time of one growth. And we'll see how that works in a minute when we do an example. Here's just a couple quick examples of what an exponential function looks like. We can tell it's an exponential function from the equation because the variable is now in the exponent. And basically this function, the one in red, is the function y equals 2 to the power of x. That means if we look at our y values go from, when x is 0, it goes from 1. When x is 1, it then doubles and goes to 2. When x is 2, it doubles again and goes to 4. When x is 3, it doubles again and goes to 8. And then finally, 16. So notice there's a common ratio between the y values. They're repeatedly doubling. Not a common difference. A common ratio between the y values repeatedly doubling. And if we look at this function, y equals 1/2 to the power of x, if we look at consecutive y values, it goes from 16 to 8, then 4, then 2, then 1, then 0.5, then 0.25, and so on. They're repeatedly getting cut in half because the base of a power is 1/2. So that's what those functions look like. Let's do a couple examples. So these are what the examples for the exponential functions questions usually like. A bacteria culture starts with a population of 12,000, so that's our initial value, that's our A. It doubles every 4 hours, so it's repeatedly doubling, so that's our growth factor, that's our B. How many bacteria are present after 12 hours? So Y is always our future value. It's equal to the initial value, and that initial value is going to be repeatedly doubled. How many times is it going to double in 12 hours, right? It doubles once every 4 hours, so how many times will it double in 12 hours? Well, the x value on the exponent is always equal to total time divided by time of one growth. So total time is 12, time of one growth is 4. So 12 over 4 is 3. So if we were to evaluate this, so we need to do 12,000 times 2 to the power of 3. So if you're to use your calculator, so what we need to do, 12,000 times 2 to the 3, well 2 to the 3 is 8. So I'll just write it like this, and we get 96,000. So y equals 96,000. So that's the amount of bacteria that would be present after 12 hours. Let's work backwards. This time it tells us the future value. So we know there's going to be 49,152,000 bacteria present at a certain time period. How long will it take for there to be that many bacteria? So it started at 12,000, and it was doubled once every 4 hours. So I need to do the total time, which is unknown, divided by 4. So notice our unknown is in the exponent. It's a little bit difficult to solve for this when the unknown is in the exponent, but we can start by dividing this 12,000 to the other side. So do this 49 million divided by 12,000, and we would get 4,096 equals 2 to the power of t over 4. A couple of different methods to solve from here. First, we could try and rewrite 4,096 with the same base as this. We could write it with the base of 2. You might have to do some trial and error to figure out that 4,096 is equivalent to 2 to the power of 12. So we could rewrite 4,096 as 2 to the power of 12. And now that we have two powers with a common base, we know that their exponents must be equal to each other. So we could write 12 equals t over 4, and then 48 equals t. So it would be 48 hours. Another way to try and avoid having to do a little bit of trial and error is you'll learn log rules in advanced functions, but basically there's a little bit of trick we can do here. If we do log of 4,096 divided by log 2, that will tell us it'll tell us what power we would have to put onto the 2 to make it equal to 4,096. So it'll tell us what is equal to t over 4. So we can do log 4,096. I'll just show you to show you that it works here. Log 4,096 divided by log 2, and you'd figure out the answer is 12. So we get 12 equals t over 4, and we get 48 equals t. So you'd write your sentence. It would take 48 hours for us to have a population of this 49,152,000. Next section, so we're almost done, discrete functions. So discrete functions basically look at sequences and series. So a sequence is just an ordered list of numbers identified by a pattern, and a series is when you add all those numbers together. So graphically, this is what a discrete function looks like. It's just a bunch of points that aren't connected. So if I were to list out the y-coordinates of these points, it would go 2, then 6, then 10, then 14. This is what we call a sequence of numbers. This is a discrete function. You would just list the y-coordinates. So the first point has y-coordinate 2, second 6, and so on. And there are two main different types of sequences we look at. We look at arithmetic and geometric. These formulas, so for an arithmetic sequence formula, it tells you a formula to be able to get the value of any individual term in a sequence. For arithmetic sequences have a common difference, right? They go up by the same amount each time. So like this one, it went up by 4 each time, so we'd say that's an arithmetic sequence. It has a common difference. To get any term, you take your first term a, and you add the common difference n minus 1 times. If you have a geometric sequence, that means there's a common ratio between terms. So, for example, it could be the sequence 2, 4, 8, 16. Basically what's happening, it's not a common difference between terms, but a common ratio. The ratio between terms is a factor of 2, so multiply by 2 each time to get the next term. The common ratio would be 2. A is still your first term, and to get any individual term, you take your first term, multiply it by the common ratio n minus 1 times. The series formulas are if you want to add all the terms together in a sequence. So these formulas would tell you the sum of n terms in an arithmetic series. So series means we're adding the terms together. Sequence is just this formula will give you one individual term. For an arithmetic series, we have two formulas. Use this one when you know the value of the last term of the series. Use this one when you don't. Geometric, if you want to add up all the terms in the geometric series, you would use this formula here. Let's look at what the questions look like. So I've given you two sequences. Let's determine whether it's first arithmetic or geometric, and then write a formula for the general term in the sequence, so a formula that could be used to find any term, and then use that formula to find the 12th term. So first of all, between terms here, there's a common difference. To get from term to term, you just add 6. So that tells us what we have is an arithmetic sequence. What I'm going to do to write my formula, it's equal to a, which is our first term, plus n minus 1 times the common difference, which is 6. So that formula can be used to find any term we want. Let's use it to find term 12. If we want term 12, we would start with 9 and add our common difference of 6, 12 minus 1 times, so 11 times. So 9 plus 66, that would give us 75. Our 12th term would be 75. This one, there's not a common difference, right? It goes up by 3, then down by 6. Okay, so not a common difference, but a common ratio. I could multiply by -2. To get from here to here, multiply by -2. To get from here to here, multiply by -2. So we have a common ratio. So this one is geometric. So our formula for the general term is equal to the first term, -1, multiplied by the common ratio, -2, n minus 1 times. So if we want the 12th term, we would have to multiply -1 by -2, 12 minus 1 times. And if we go ahead and do that, we would get term 12 equals 2048. How about this? Find the sum of the series. So now the terms are all being added together, so we now have a series. If we want the sum of this series, we'd first have to know, okay, this ... means we skipped a bunch of terms, right? The first term is 251, then there's 243, and it skips a bunch, and then we get to -205. So if we're going to find the sum of this series, we first need to figure out, okay, how many terms do we have in this series? So what term number is -205? So remember, and also this is arithmetic, right? It's going down by 8 each time. So it's a common difference, so it's arithmetic. Our formula for any individual term in an arithmetic sequence is a plus n minus 1 times d. Well, we know the last term is -205, so we know the value of the term. So I know the value of the term is -205. I know the first term is 251. I don't know what term number it is. But I need to figure this out. That's the main thing we need to figure out before we can do anything else. And I know the common difference is -8. So what we have to do now is we have to solve this equation for n to figure out what term number is this. So first subtract that -251 to the other side, and we get -456 equals n minus 1 times -8. Divide your -8 to the other side, and we'll get 57. And then add your 1, 58 equals n. So this is the 58th term. So now that we know what term number it is, we can go ahead and find the sum of those 58 terms using either of these two formulas. This formula is going to be easier since we know the value of term 58. So if we want the sum of 58 terms, if we know term 58, this formula is a little bit easier to use. So if I use that formula, the sum of 58 terms, it's equal to n over 2 times a plus term 58. And let's plug in everything we know. So n's 58, so 58 over 2. Our first term is 251 plus term 58 we know is -205. So minus 205. And then all we have to do is go ahead and evaluate this. So we'll get 29 times 46. And that gives us 1,334. So that would be the sum of the first 58 terms in this series. In discrete functions, another way to show the relationship between terms in a sequence is what's called a recursion formula. A recursion formula, to find a term, you use the previous term. Term. So to find term n, you would have to use the term 1 before n. We'd write that as term n minus 1. And then do some operation to that previous term. So let's use this recursion formula to write the first 4 terms. So the recursion formula has to tell you the first term. So it tells us term 1 is -6. If we want to find term 2, look what happens when we use the formula. If we want term 2, it's equal to term 2 minus 1. Well, 2 minus 1 is 1, so it's equal to term 1 plus 5. So you use the previous term and then do an operation to it. Well, term 1 I know is -6, so do -6 plus 5. That gives me -1. If I want term 3, I do term 3 minus 1, which is term 2, add 5. So you do the previous term plus 5. Term 2 is -1, so -1 plus 5 is equal to 4. And term 4 is equal to the previous term, so term 3 plus 5. Term 3 is 4 plus 5, 9. So my first 4 terms are negative 6, negative 1, 4, and 9. Each term is equal to the previous term plus 5. So it's a recursion formula. If in the formula you use the previous term in the sequence to get the next term. Last section of functions.